Determine the shear and moment in the beam as functions of x. To solve this, first we can convert our distributed load into point loads. First one will be the rectangular, so it's going to be W0 times L over 2. The other one is going to be W0 times half times L over 2. And then our external reaction forces, so there's going to be 3 here. Horizontal will be 0. Vertical we can find by summing the forces in y direction. We're going to have positive AY, negative W0, L over 2 and negative W0, L over 4 all equals to 0. Solving for AY, get our solution as 3 over 4 W0L. Similarly, the moment will be taking moment about the point A. We're going to have W0L over 2 times L over 4 negative, and then clockwise L times W0 over 4 times L over 6 equals to 0, and negative ME. And finally, a moment will be negative 27 over 4, 7 divided by 0.4 W0 L squared. Now we can recognize here that there are two regions that needs to be solved separately. For region 1, our load equation is simply negative W0. Our shear for region 1 is going to be negative W0x plus C, which is our constant. And to find our C, we know our shear is going to be 3 over 4 W0L when x is 0. Therefore, this is our C. Rewriting our shear equation. And then finally our moment. Equation is going to be integral of here. So it's negative W0x squared over 2 plus 3 over 4 W0Lx plus C. And now to find our constant, we know our moment is going to be negative 7 over 24 W0L squared when x is 0. So this is our C. Rewriting our moment equation. Negative W0x squared over 2 plus 3 over 4 W0Lx plus our constant, which is negative 7 over 24 W0L squared. Now we can proceed to region 2. Region 2, first of all, we need to find our load equation, and to find our load equation, we need to use proportionality. So we know W0, which is negative, happens at 7 over 2 distance, and we know it's going to be 0 when distance is L. Similarly, you're going to have, negative W0 happens at 7 over 2, and we don't know what happens or what our load is when the distance is x. Now let's simplify. We can have negative, which will become positive, 2 times W0 divided by L equals to negative W0, negative Y, positive L over 2 take away x. Now we can cross multiply. When we cross multiply L over 2 negative x, we're going to have 2 over L times W0 times L over 2 take away x equals to negative W0 negative Y. Now let's multiply and simplify it. So we're going to have W0 take away 2 times W0 times X divided by L equals to negative W0 negative Y. Now we're going to add W0 both sides. We're going to have 2 W0 take away 2 times W0 X divided by L equals to negative Y. Now we're going to multiply both sides by negative. We're going to have positive 2W0X divided by L take away 2W0 equals to Y. And this is our load equation. It's going to be positive 2W0X divided by L take away 2W0. Now we're going to take the integral of this, and we're going to have W0X squared divided by L take away 2W0X plus the constant. And for our constant, we know our here is going to be 0 when as X is equal to L. Therefore, our equation is going to become something like this. And simplifying it further, you're going to be left with positive W0L equals to C. Now we're going to plug the C into our shear equation. It's going to be W0X squared divided by L take away 2W0X plus W0L as our shear equation. Now we're going to take another integral for our moment equation. So our moment equation is going to become W0X cubed divided by 3L take away W0X squared plus W0LX plus the constant. And again, we know our moment is going to be 0 when X is L. So we're going to have W0 divided by 3 times L squared take away W0 L squared plus W0 L squared plus the constant. These two cancel each other out, and we're left with C as negative W0 L squared divided by 3. And now we can plug this value of C into our moment equation. So we're going to have our moment for region 2 as W0X cubed divided by 3L take away W0X squared plus W0LX. Determine the shear and moment in the beam as functions of X. Second part, determine the shear and moment diagrams for the beam and determine the shear and moment in the beam as functions of X, where 4 is less than X and X is less than 10 feet. The second part of this second part will be solved in first part. All right, to begin, first of all, let's convert our distributed load into point load. So it's going to be 150 times 6, which comes up to be 900 pounds. And then our external reaction forces, A is a ruler, B is a pin. For B, X is going to be 0, the horizontal force. By we'll have to calculate still. And we have to recognize that there's going to be 3 different regions where the force fluctuates. Solve this problem. First of all, let's take moment about the point B to find our solution for AY. So we're going to have clockwise 200 pound foot given moment. Then we have counterclockwise 900 pounds, and it's 3 feet away. Then we have our AY clockwise 6 feet away. And finally, we have counterclockwise 200 pound foot moment given. All of this is equal to 0. The moments cancel each other out, left with 9 times 3, which is 27. 2700 divided by 6 is 450. So our AY is going to be 450 Newton positive, pounds. And then now we can solve the forces in y direction to find a solution for By. So we can have AY, which is 450 pounds, negative 900 pounds, and positive By, all equals to 0. Solving for by, we get a solution as another 450 pounds. So this means this beam is balanced on these two spouts. All right, so now let's determine the shear moment of the beam. All right, so to begin for the region 1, we have our load equation as 0. This means our shear is going to be simply our constant. But we know that when x is 0, shear is 0, so c is 0. And finally, our moment is going to be counterclockwise, so this means it's going to be c, which is going to be negative 200 pound-foot. For our region number 2, our load equation is going to be negative 150 pounds per foot. And then taking the integral, we're going to have negative 150x plus the constant. We know that our shear is going to be 0 when x is 4. And solving for c, we get our solution as pardon me, I forgot one thing. We do have 0 from the region 1, but we also have ay, which was 450. Now, when we solve for c, we get our solution as 1050. We're going to plug the value of the c into our shear equation, and it's going to become negative 150x plus 150. Now we're going to take another integral of the shear to find our moment. So we're going to have negative 150 x squared divided by 2 plus 1050x plus the c, which is our constant. From region 1, we know that our moment is going to be negative 200 when x is 4. So it's going to be negative 150. 4 squared is 16 divided by 2, and then 150 times 4 plus c. Solving for c, we get our solution as negative 3200. Now we're going to plug this value of c into our moment equation. We're going to have negative 150 x squared divided by 2 plus 150x. Take away 3200. Now we'll begin our region 3. For region 3, our load equation is again going to be a 0. And taking the integral, get our shear equation, it's just simply going to be a c. And to find the value of c, we know shear is 0 when x is 14, so c is 0. And finally, taking the integral of the shear, we're going to have our moment equals to c, and we know our moment is negative 200 when x is 14. Therefore, our moment is going to be negative 200. Now, the second part of this equation, or the problem, I'm going to move these. Let's draw our, first of all, shear diagram. So our shear begins at 0 all the way till 4 feet, where it will go up or into the positive fraction. You can see 450 pounds. Let's say this is our 450 pounds. So we're going to begin at 0, continue at 0, then go up to 450 pounds. and then all the way till B, or 6 feet, we can go downwards 900 pounds. So this will become negative 450. It's going to be straight line. And then from there, we're going to have to go up 450 because our BY is 450. Will get us to 0. And then we go all the way to 14 pound or 14 feet. And there is no moment in the shear curve. Now for the moment we're going to start at negative 200, and then there is no moment till 4 feet. We're going to go continue at this phase, and from there you're going to have a second order curve, and before we can decide how long is this region or how much is this region, we have to find out where this intersect is. To do that, we have to use our region 2 shear equation, which is right about here. I'm going to bring it down, so it's going to be, so it is negative 150x plus 1050, and we want to know what is the value of the x where shear is 0. To do that, gonna subtract both sides by 1050 and then divide both sides by negative 150. When we do that, our value comes up to be 7. So this means we intersect at 7. All right, now that we know where the intersection is, this is where the concavity of our moment curve will change. So now we have to determine what is our moment at this point. So for that, all we have to do is plug in the value of x into our moment equation for region 2. We're going to have negative 150 times 7 squared divided by 2 plus 1050 times 7, take with 3200. So in this, we get our solution as 475. So that means our curve will go all the way to 475, and it will be concaving downwards. Then from there, we need to know how much down this curve is going to go down from here. There are two ways to do it. We're going to continue using our formula here. So this means we're going to plug the value of 10x. When x is 10, it's going to be 100 divided by 2 plus 1050 times 10, negative 3200. Solving this, we get our solution as negative 200. So this means over at this point, our curve is going to concaving downwards and come all the way to 200. Then there's no motion in the curve till the end, where it's going to go up by 200 points or 200 pounds. And